Thank you, and pleasure to be here. Thanks for the opportunity, and really looking forward to these discussions. So I'm a physical scientist at NASA's Goddard Space Flight Center. I'm a freshwater scientist. I mostly focus on, like Francis was alluding to, looking at the global picture and how water cycle is changing, less on solutions. I'm here to learn from you all on that. So we've already made the case of why freshwater is sort of precious here. You know, we only have 2.5% of all the water on the planet, and of all that, most of it is locked up in glaciers and ice caps, and we have a lot of the remaining water, which we call as green water, stored as groundwater. And so actually the amount of fresh water we have available is the amount of surface water we have available is very, very little. So in fact, Earth, among all the other planets, Earth is pretty unique because this is the only planet we have so far where we have water in all the three forms: gas, liquid, and ice. So again, I found this neat graphic that again puts this in perspective. If you compare the volume of water we have to the volume of Earth, the entire amount of water we have is 1,000th of Earth's volume. And you can see that smaller sphere, which is the amount of fresh water we have. And if you can really squint your eyes, there is a little blue dot right above Atlanta. That's the amount of actual surface water we have. And I think some of the previous speakers made this point. And this is exactly why studying water and its variability is important, and the distribution. When we have less water than we expect in the places where we want, that's where when we have scarcity, and when we have more than what we want, when we have extremes like floods. So I'll show a few very high-level insights on how NASA looks at this problem and some of the key insights we have found. So as you know, NASA has a fantastic array of remote sensing platforms that look down on the planet and study all kinds of things. So this schematic shows NASA's water cycle fleet, which lists the number of current orbiting and these platforms that are planned in the future. So together, these platforms provide really an unprecedented look at Earth's water in our atmosphere, on the land surface, and in the oceans. And again, using the data from these satellites, we try to quantify the variability of our Earth's water. So one of the oldest and longest program is called Landsat, which I'm sure you're familiar with. The first Landsat satellite was launched in 1972, and we are on the 9th one in the series, launched in 2021. And Landsat has provided imagery of Earth's surface and really a visual confirmation of the impact that we've had on the planet. So I'll show a couple of examples. This is RLC. I think Carlos mentioned this earlier. This used to be the world's fourth largest freshwater body, and it was so large that we called it sea, right? And now it has shrunk so much in volume, 60% in volume, 80% in volume, and 60% in terms of surface area. So Landsat has been able to provide a confirmation of that. Lake Mead, I know you sort of stole my thunder. So this is the largest reservoir in the US, provides water to 40 million people. Again, the Landsat imagery confirms this. This is the picture I was going to show my daughter in front of the reservoir last year. You can really see Yale again made this point, the bathing effect, that shows that the reservoir has shrunk to below 35% in its capacity. This is an example in Spain. And again, in Spain had an unprecedented drought in 2023, the driest year on record in the last 110 years, second only to 2022. And again, Landsat here shows the Sao reservoir, and that rapid depletion in water that you can even observe from space. Again, that bathing effect was captured within a matter of a few weeks. So in addition to Landsat, NASA has, again, a lot of different satellites that measure all kinds of properties about the freshwater, the water cycle. So NASA, this is an animation of the global precipitation and snowfall changes measured from NASA's Global Precipitation Measurement Satellite. So in fact, this is a constellation of satellites with NASA providing the core observatory and the other satellites from partner agencies. So by stitching this information together, we can look at rainfall and snowfall every 30 minutes on the planet. So once the rain falls on the ground, it comes onto the land surface, and some of it infiltrated into the soil. So the amount of water we have in the soil, called soil moisture, is a very important variable for a lot of different applications, for weather prediction, for agriculture. So NASA has a satellite called Soil Moisture Active Passive Mission that measures the soil moisture on the surface. So this animation shows both the data from GPM, you can see the rainfall patterns and how the soil moisture responds. You just saw Hurricane Florence pass by, and then how the soil moisture responds to all the rainfall that you have. This is another animation that I love from, I don't know, can you make it play? So this is a pattern of vegetation changes that we have from remote sensing platforms. So if there's animation, yeah, there you go. So when it plays, it really shows an annual cycle of vegetation, right? So you can see the northern hemisphere, the summer, and the planet, the entire northern hemisphere greens up, and then in the winter, it all goes to the southern hemisphere. When I see this animation, to me, it's like Earth breathing in and out, right? It really shows it because vegetation activity is so tied to CO2 emissions and also water. So this is another key measurement we have. A very similar one on snow. It's a huge water storage term for our planet. This is, again, an annual cycle of snow cover observed from some of our optical instruments. That shows how the snow builds up during the winter in northern hemisphere, and it all recedes in the summer time frame. It also gives you a perspective of how important snow is for particularly the northern hemisphere for water storage. So another satellite, this has really revolutionized how we look at freshwater. It's called Gravity Recovery and Climate Experiment. So this is, in fact, twin satellites. We call them Tom and Jerry. They actually follow each other on the planet. It's very different from all other NASA's satellites in that most of the satellite exploit some sort of electromagnetic signal, but GRACE is really these two satellites about 220 kilometers apart, and they're kind of following each other. And the key measurement is the distance between them. The neat thing is the distance between them changes slightly in response to Earth's gravity field. And GRACE measures very precisely with GPS and laser systems the changes in these distances. And then the response to the gravity field is really because of changes on the mass on the Earth's surface. So if you're standing on top of the Mount Everest, you'll weigh slightly different, right? So we can then sort of back out what's causing these changes. And many of these mass changes are happening because of changes on Earth's water, either because of ice melting and when we pump out water from aquifers and whatnot. So by stitching these data sets together, not just from GRACE, but also from other satellites, now we can start to understand the local variations in Earth's water. So this map kind of shows the regional changes in water cycle storage, and the red colors indicate where we have deficits compared to long-term averages, and blue colors indicate when we have excess compared to long-term averages. So again, by looking at all this data that we have about multiple aspects of the freshwater cycle, we can start to attribute these changes to natural variability, human activity, or climate change. So for example, if that big signal do you see in Greenland, it's because of the melting you have from climate change and the warming. When we go over to California, we've had significant droughts in recent years. And because of that, there's been an increased reliance on groundwater resources. And we can see that from GRACE, that significant depletion that has happened in California, and Francis mentioned in places where you have subsidence. So that's a clear indication of human activity contributing to these changes. If you go over to southern Africa, this is a very different picture in the Okawanga Delta. You can see the significant increase in water storage. And that's, again, been confirmed when we look at the rainfall data from GPM that shows that we've had increasing rainfall patterns in this southern Africa that has helped to replenish the aquifers in that region. Another example would be over Saudi Arabia, where, again, if you look at the changes in water storage from GRACE, you can see a systematic decrease. And this has been attributed to agricultural irrigation. So the data from Landsat shows how the agriculture has expanded in Saudi Arabia, exploiting the groundwater aquifers. So in 2014, the government changed the policies to reduce some of the refarming practices. And then, sure enough, we see the aquifers kind of showing a slight uptick in the storage. That's observed from GRACE. So again, with this type of analysis has been conducted in many places in the world. I'm just showing a couple of examples. So again, this point was made by David and others that agriculture is sort of the elephant in the room in terms of the freshwater usage. More than 70% of freshwater usages for agriculture, with industrial and municipal uses only a distant second and third. So obviously, how we use water for agriculture has huge impacts. And I just want to show one example from Bangladesh, which is obviously a developing country, huge population. So that chart shows the rice productivity from some of the major rice-producing nations. So Bangladesh ranks third, right next to India and China. And they've had a huge increase in rice productivity in the last few decades, mainly to keep up with the growing population. They've even had an off-season agriculture now. And this comes at the expense of groundwater, because all the water for rice production comes from groundwater. So when we piece all the data together in terms of how much rainfall we have and how much groundwater has been pumped out, it shows a sort of a grim picture for Bangladesh. The majority of the country shows huge decreases in groundwater storage. It's also, the country is also facing challenges in terms of sea level rise and encroachment and all that. In addition to water availability, we also can look at changes in extremes. This is the work of my colleagues who stitched together a lot of, again, remote sensing data sets to look at how the global intensity of wet and dry extremes have been changing. And this is a simple graphic that clearly demonstrates that the intensity, we are having more extremes, both wet and dry extremes. So thinking about the future, there's a lot of literature out there. So I just sort of want to show this graphic that sort of summarizes what we expect, right? So IPCC has compiled the data from climate models that looks at different scenarios of greenhouse gas emissions. That leads to different levels of warming. So the 1.5 degrees is sort of the target that we set from the Paris Climate Agreement. So, and when between 1.5 and 2 degrees, which we are getting closer to, we expect a lot of reduction and scarcity in terms of water shortages. At 3 degrees, the picture becomes very serious because the Himalayan glaciers are expected to have significant melting. This is a huge concern, particularly in that region with a tremendous set of population. And obviously at a 4-degree, everything, hell breaks loose. So, like I said at the beginning, I'm not an expert in solutions, but I wanted to kind of at least give a couple of perspectives on that. This is a schematic I borrowed from my planetary science colleagues, which kind of shows the amount of water we have in other planets. So in terms of, this is a picture mostly from our own solar system, looking at other planets and the moons. There's also similar schematic for exoplanets, but basically the idea is we have found water in other planets, but most of it is in basically ice forms. There's only one moon where we have found liquid water. It's on Titan, I believe. It's a moon of Saturn. But that water is basically ethane and methane. When it's super cooled, it looks like water. It's not really water as far as we can use for consumption. So the point I want to make is there's no replacement for our planet. There's no other planet B, right? We are making progress in terms of exploration, but we are looking at hundreds of years of really finding sustainable water in other planets. I just want to end with this story, which is a hopeful one. Long back, you all remember the story of the ozone hole when the scientists on the British Antarctic Survey first found the problem, and then actually NASA had an instrument called AURA that actually provided confirmation of this over the last 2 decades. But then the scientific and the international community came together in 1987. The Montreal Protocol was signed. And that chart here shows the result of that, right? So we basically, that agreement led to eliminating the ozone-depleting substance that we have been producing. And it's been a significant achievement. And there is now evidence that the ozone layer is on track to recover. So we need something similar for the Earth. So this is the iconic picture of what is known as the blue marble that was taken by the astronauts on the Apollo 17. This, I think, is the most reproduced image, I believe, one of the most reproduced images in human history. It's so beautiful, right? I mean, this really shows the beauty of our planet, the frailty of the resources that we have. So I want to end on this sort of hopeful note, and I was reading New York Times the other day. I think there was, for the first time, there's reports that now the greenhouse gas emissions are decreased compared to the previous year, 2020, in 2023 compared to 2022. Basically, there's some hope, I think. So I'll end on that note.